Hey everyone, and welcome. You know, in science, we're always chasing after precision, after the absolute truth. But what if I told you that the secret to getting closer to that truth is actually embracing imperfection? Today, we're going to dive deep into the concept of scientific uncertainty, and it all kicks off with one simple question.
Really think about that for a second. Whether you're using a ruler, a super accurate digital scale, or a high-tech laser, can you ever get a 100% exact value? The honest answer, the scientific answer is nope. Every single measurement we ever make has limits. And that's not a failure, it's just a fact of life.
And this is why when a scientist talks about error, they're not saying, oops, I messed up. Not at all. They're actually making a really powerful statement about the precision of their tools and the boundaries of what they know. Error is the language we use to be honest about how confident we are in a number.
So if every measurement is a little bit fuzzy, how in the world do scientists handle that? Well, they've developed some really clever tools to actually put a number on that fuzziness.
Okay, so the first one is the most straightforward. It's called absolute error. Let's say you measure a pencil to be about 15 centimeters long with a regular ruler. You might write that down as 15.0 plus or minus 0.1 centimeters. That plus or minus 0.1 part, that's your absolute error. It's basically the window where the true perfect value most likely lives.
But here's the thing. An absolute error of 0.1 centimeters doesn't tell you the whole story. For that, we need something called relative error. This is what puts the uncertainty into context, because it compares the size of the error to the size of the thing you're actually measuring. In other words, is that 0.1 centimeters a huge deal, or is it basically nothing?
And this is where it all just clicks. Think about it. An uncertainty of just 1 single millimeter would be a massive deal if you're a biologist trying to measure an ant. That could be a huge percentage of its entire body. But for an engineer measuring a skyscraper, that same 1 millimeter error is completely, utterly insignificant. Relative error is what tells us if our uncertainty actually matters.
So, we've got these two types of error, absolute and relative. Let's put them to the test with a classic lab challenge, trying to calculate the density of a small block.
So, quick refresher, density is just how much stuff or mass is packed into a certain amount of space or volume. And the formula is super simple, mass divided by volume. But notice, to get density, we have to combine at least two separate measurements. And that, my friends, is where things get really interesting.
All right, here's our setup. We've got a digital scale that we know is precise to within 0.1 grams, and we've got a ruler that's precise to within 0.1 centimeters. Our mission, should we choose to accept it, is to use these imperfect tools to measure our block and figure out its density as honestly as we possibly can.
And this brings us right to the heart of our problem. When you take a bunch of imperfect measurements and you start combining them in a formula, their little individual uncertainties don't just magically disappear. Nope. They combine, they grow, and they spread. Kind of like a ripple in a pond. This is what we call the propagation of error.
So let's ask the key question. If I add, or subtract, or multiply, or divide a bunch of numbers that each have their own little cloud of uncertainty around them, what happens to the uncertainty of my final answer? Does it get bigger? Does it get smaller? Does it just average out somehow?
Well, it turns out there are some very specific rules for this. And for the simple stuff like adding or subtracting, the rule is super easy. You just add their absolute errors right together.
For instance, let's say we have one measurement of 5.0 and it has an uncertainty of 0.2.
And we add a second measurement of 3.0 with a smaller uncertainty of just 0.1.
The rule is simple. The absolute errors just add up, giving us 8.0 with a new, bigger uncertainty of 0.3. So here's the crucial takeaway. Our final answer is now more uncertain than either of the individual pieces. The uncertainty has grown.
But, and this is a big but, for multiplication and division, the whole game changes. And this is so important for our density calculation, right? Because that's mass divided by volume. In these cases, it's the relative errors that you add together. This is a clever way to make sure a tiny measurement with a small absolute error doesn't unfairly blow up the final uncertainty.
All right, we have our rules for how errors combine. We have our mission. Now we have everything we need to solve our density challenge and find the true, scientifically honest answer for our block.
So here's our game plan. First, we got to calculate the volume. That's length times width times height. All multiplication, right? So step 2, we're going to have to find the relative error for the volume by adding up the relative errors of our 3 length measurements.
Then, step 3, we calculate the density, mass divided by volume. And because that's division, we do it again. Step 4 is adding the relative error of the mass to the relative error of the volume we just found. And finally, we can convert that back into an absolute error to give our final honest answer.
And after running all the numbers, this is what we get. The density is not just 2.1. The true, honest answer is that the density is somewhere in the range of 1.9 to 2.3 grams per cubic centimeter. We didn't just calculate a number, we calculated our confidence in that number.
So that little plus or minus 0.2 isn't a sign of a bad experiment. It is the exact opposite. It is a confident, bold statement about what we know and exactly how well we know it. That, right there, is the signature of good science.
So why did we spend all this time on plus or minus values? You might be thinking, okay, that's cool for a science lab, but why does this matter to me? Well, because understanding and calculating error isn't just some academic exercise. It is absolutely critical to how the entire modern world functions.
Every single time an engineer designs a bridge, they use tolerances, a calculated margin of error. Every pharmaceutical company has to prove a drug's dosage is safe and effective within a tiny error margin. You know that margin of error you always hear about in political polls? That's exactly what we've been talking about. Climate models, your phone's GPS, literally thousands of things you rely on every single day are built on a really sophisticated understanding of uncertainty.
So I'll leave you with this final thought. We are surrounded every day by numbers that seem so absolute, so perfect. But now you know the secret. Behind every single one of them, there's a hidden story of uncertainty. The world isn't really as black and white as it seems. It's painted in all these fascinating shades of probability. And once you start seeing the world that way, you realize it's a much more interesting and a much more honest place to be.